This is an analysis of problem H called Pachinko from the ICPC World Finals 2014. The problem is about a game called Pachinko machine, which resembles pinball a lot, but in this case it is a little bit different. So in the game we have a rectangular field W times H, where W is small, up to 20 for example, in this problem, and H is big, up to 10,000. And in each square of the rectangular field there is either a peg, an obstacle, or a target. And the aim of the game is to get the ball into the target. The ball starts by dropping from the top, and then it randomly bounces off the pegs, so that if it comes into the square where there is a peg, then it randomly bounces either up or down, or to the right or to the left, and the probabilities are given for each of those directions, and they are the same for each peg. So there is one probability called D to go down if a ball comes into any peg, and it goes down with probability D from any peg it comes to. And the same is for going up, probability is U, for going left, the probability is L, or for going right, the probability is R. And those four numbers sum up to 1. So ball always bounces off in one of those four directions. The ball cannot get into obstacles, so if there is an obstacle in a square, then it can't get there even if it has to bounce off the peg. And also, if the ball comes into the target, it doesn't bounce anymore, it just stops and the game ends at that moment. So the task at hand is to compute the probability of hitting each target. We know exactly that after the game ends, the ball is in one of the targets, so the probabilities of hitting each target sum up to 1. But we need to know exactly what are the probabilities for each of the targets. Basically, there is no player in this game, there is only a random process, and we want to find in which target it is most probable to end. So the solution goes like this. For each square ij of the rectangular field, we will compute S of ij, which is the expected number of times the ball will come to the square. Of course, the ball can never reach some squares, it can come once or more into the other squares, and for each square independently we will compute the expected number of times the ball hits this square. To compute those expectations, we will have to solve a system of linear equations. The equations will look like the one on the slide, but there are some corner cases which we should account for. So for example, if a neighbor is a target, then the ball cannot come to our square from this neighbor, because as soon as the ball gets into a target, it stops. So it cannot come to our square from the target. Another corner case is that if a square has an obstacle in it, then the ball cannot get in it, and so the expectation will be equal to 0. So the system of equations will look mostly like the equation on the slide, but in some of the equations some of the summands will be absent, and also some of the equations will be absent themselves. Those are the equations for the cells which contain obstacles. We also know that only one of the targets will be reached, and exactly one target will be reached, because the ball cannot bounce off infinitely. We know from the problem statement that after at most 1 billion steps the ball will definitely come into one of the targets, and we know that as soon as it comes to a target it stops, so we know that exactly one of the targets will be reached. And so each target will be reached either one time, if this is the final target that the ball reaches, or 0 times if the ball never comes into this target. So for each target, if it is in square ij, S of ij is equal to P of yj, where P of ij is the probability of hitting this target. And why is that? Because P of ij is the probability that the ball comes to this target. And when the ball comes to this target, it stays there. So either the ball doesn't come to the target at all, and that gives a 0 summand to the expectation, or it comes to the target once with probability P of ij, and this gives the summand P of ij to the expectation. There are no other summonds in the expectation because the ball cannot come to the target more than once. So for the targets, the expectations are equal to the probabilities that we want to find. And thus, if we solve the system of linear equations and find all the expectations, we will subsequently find the probabilities of hitting each target, just copying the expectations we found for those squares. So, the system has up to 200,000 equations with 200,000 variables. That's the number of squares in the field. We have a variable, an expectation for almost all the squares in the field, probably all of them if there are no obstacles in some test. And we have an equation for each of the cells, which is about the expectation of the number of times that the ball comes to this square. So the system can be really big, and so we cannot solve it with the usual Gaussian elimination. We have to optimize. So the main optimization is to remove the squares which are unreachable from the top, because we don't need to compute the expectations from them. We know that the ball will never reach them, and so there is no point in spending some time and eliminating variables in that part of the matrix. So we just start with a breadth first search, for example, that will find all the squares that are reachable from the top and discard all the others. And so we will decrease the number of equations and variables this way. Then what we should mention is that the matrix of the system is sparse initially, because for each equations only 4 other variables other than the variable for this square have non-zero coefficients. So in each line, which may have like 200,000 variables, only 5 of them have non-zero coefficients. And due to the structure of this matrix, we can prove that if we just do regular Gaussian elimination, the matrix will still stay sparse. And so actually we can do Gaussian elimination on this matrix, and if we do it like not with the square matrix which is stored as a square array, but if we store it as a sparse matrix, when we store only the non-zero coefficients, and we do all the elimination while still storing the matrix as a sparse matrix, then the Gaussian elimination will work fast enough, and we can do both forward and backward pass of regular Gaussian elimination with this sparse matrix and solve the diagonal system which we get after forward and backward pass of Gaussian algorithm. And then when we have the diagonal system, it's trivial to solve the system and to get all the expectations and subsequently the probabilities that we need.